Video we have actually last two video we actually derive what are the things that are given. Okay, we actually say that given parameters aren't much useful because comparing with the equation in the data sheets, we cannot solve anything at all, right? And then eventually we came up with the out of balance forces. Okay, where is it? A force out of balance. And then we use this formula cosine omega t. This is a 12 function you need to remember. So the key things to take note are these stuffs. Okay, this f naught and then f naught cosine omega t. These are all the things that you are not given. So these are all the very yeah. And then nonetheless we talk about this totally I don't know what the hell. Okay, and then we realize that it's pi over 2. So in fact, let's say in the exam you're given this type of questions, typically you try to guess whether it's a pi over 2 or what. But nonetheless, you should go and understand how it is being derived. And then after which you get the beta, you say that beta is equals to 1 because pi over 2, right? Based on this graph itself, pi over 2, our beta is equals to 1. So how does this help? How does this help? Okay, so this is pretty important because you only know your frequency already, your system frequency. Now you only so you can actually start finding our natural frequency, which is in fact the key to all equations. You can see everything is in terms of natural frequency, right? So natural frequency, natural frequency, natural frequency, okay? And then the damping factor also partly of the natural frequency, and then natural frequency again. So you have a lot of natural frequency. It's either natural frequency, damping factor, or whatsoever. So all in all, once you get natural frequency, you have won the lottery. So without further ado, we shall start answering the question. Okay, the first question say that find the natural frequency of the structure. Okay, find the natural frequency of the structure itself, except notwithstanding the mass itself, right? So it is in other words m minus n, right? So this is the structure. So how are we going to find it, right? So hold on a while. So we know that the natural frequency of the structure b is equals to 1, right? Is equals to omega over omega n. So therefore omega natural frequency is equals to the the system frequency, right? So this is why there are resonance, right? So therefore the natural frequency is actually 94.248 radians per second. So with this as our natural frequency, we can actually convert it to hertz, right? So because what they want is actually to find the natural frequency of the structure. So natural frequency, if you were to write in terms of radian per second, it's not that cool. So therefore, typically we would recommend you change to hertz, which is divided by 2 pi. So if you remember the period itself can be represented by 2 pi over omega n, and also can be represented by 1 over f, right? So 1 over f is nonetheless is equals to 2 pi over omega n, right? So I just bring everything here and there. You'll find that frequency can be found using natural frequency divided by 2 pi. So this is why we're doing over here. Natural frequency divided by 2 pi, you have 15 hertz. Okay, and then the second part talks about the damping ratio, right? So far what we have in the formula sheet, data sheet, you have natural frequency, you have your system frequency, you can actually find your damping factor, right? So one way is to do that method, right? So but nonetheless he didn't use this one, so maybe I should derive it. So hold on a while. So apparently he didn't use this formula is because perhaps this is not the system frequency. Okay, this is not the frequency that we're talking about, because if this is let's say 94.248, right, is equals to natural frequency because they are the same. So it equals to 1, right, equals to 1 minus damping square. Then you were to bring the square root over here, you have 1 square is equals to 1 minus damping square, right? So if you were to happen that you bring this thing, okay, I mean nonetheless if you switch this 1 over here, so it's 1 minus 1 equals to 0. In fact, there must be some damping values, right? But in this case, it's 0. Therefore, you cannot use this equation. So this frequency. So far, I said that the frequency, the system frequency. Okay, previously I said that this is equals to this. So therefore, this proves that I am wrong. So yeah. So therefore, the only way is to find using um some other formula. So it's actually this formula. Or nonetheless, this formula, right? So which formula do you want to use? So this is why we actually use this formula. Actually, you can straight away use this formula. Yeah. What the hell? Hold on. Actually, we can only use this formula. Okay. Why? We are doing things in terms of z and x, right? So if you remember, our z is equals to mx, while our this x itself is actually our mx, I think. So if you were to remember last previous few lessons, I mean few videos, we just say that mx over me, right? So we actually have our m, which is I thought that it was, you know, this m. Okay, this I thought that this is the supposedly the weight of the system, right? The mass, and then and then x is just the amplitude, right? The amplitude 21.215, and then hold on a while. And then multiplied by this amplitude, right? Divided by ME. ME we know is actually 45.9 kgmm. Okay, so I'll just do it out. So I actually solve for this portion over here. It's actually 0.49. And then since we know that beta is equals to 1, so this is 1. And then 1 minus 1 is 0. 0 squared is also 0. So 2 damping factor beta square is 4 damping factor. And then you just 4 damping, you know, factor square root, right? So we just square this thing, this one will become 4, this one will become square, right? And then beta is 1. So this is 4 damping square. And then you square root the whole system. Over the denominator you have this one. So to solve for this, okay, you just bring this portion down here, and then this one up here, and then I square root this whole thing, right? And then end up I have some values of 0.7 damping factor, which is wrong, which is the real answer is 0.0118. So in fact we cannot use this formula, right? So this what I have done earlier so far, it's wrong. Okay, wrong. Okay, so chill out a little. So we can only use this formula. Okay, so because, so to speak, is that previously we derived our f naught, right? We derived our f naught as this value 815.4, right? Out of balance f naught. Okay, so it's a little tricky. Actually, is this one. Actually, it's this one. F naught, right? So it's just mu m is omega square. So it's this one. But because we have two of the eccentric mass, right? So therefore we have to multiply by 2. So this one is 2 times 4.59, you know, that of thing. So using this one, we know that F naught is equal to 2 times 4.59, 45.9 kgmm. If we were to change, it's, you know, 2 times 45.9 times, you know, these things. So if to use this one, you would eventually get this. So just to repeat again, now I only use this formula, okay? I only use this formula, the one that we derived earlier, the force vibration, because we know our forcing function already. Our forcing In fact, this is not forcing function. This f0 is not forcing function. This f0 is just part of the forcing function. Okay, this whole thing is forcing function. F0 is part of the forcing function. So be very careful. So since we have that value as saying that this is 2.4, 2 times 4, 45.9 kgmm, okay, just straight away sub it in. So it's 2 times 407.72. So where is it? Oh, okay, sorry. Hold on a while. Because this is sorry, this is just ME. Okay, we lack of the omega square. Remember, we didn't solve for it yet. So this is actually the real value, 2 times, this one, ME omega square goes to F0. And then times 2 because we have 2 is something less. So this is just my class mistake, okay? So hope that I didn't confuse you. So in other words, this is still the same. This value is actually equals to this, okay? This whole thing is equals to this. Just that because I didn't write properly. Okay, it should be have like multiply omega squared that thing, right? So actually I didn't do it properly. But nonetheless, you should understand. So I just sub in my f0 and then divided by k because we have the formula over here stating that things, right? So we don't know our k, right? But we know our natural frequency. We know our natural frequency, so we can actually, and we know our mass, so we can actually straight away sub in. So where is it? So we have mass of the structure times omega n squared, natural frequency squared, as k. So we just sub it in over here, right? Because this is eventually this is denominator, right? So hold on. So you can actually rewrite this f naught over k by this one. So you just bring this k downwards. Okay, if you remember. So this k in this case is actually this m omega square. So you just sub it in. So you have m. Sorry, this is the big M omega n square, and then to the main factor. You know that okay. So this is 2m the main factor omega square. So they are the same. So this 2 multiplied by m omega square, and then we have some x. Hold on. You know why? It's because it's equals to x, right? This whole thing is equals to x. So apparently I just bring, because I want to find out the main factor, right? So I'll just switch. I just bring this the main factor up, and I just bring this x down. So we have this portion over here. So this is where this is the same as this, right? So now you can sub in the values. You know your f0, you know your mass, which is 1.45, you know natural frequency, and you know your amplitude x. So you just do it out. Eventually you can get your 0.018 Fleming ratio. Okay. So I'll just stop here for part 2, B. So for the next video I'll just do C and D, and then we'll do a summary and that's it. Right, so I'll just see you in the next video.